Sweet. Welcome to the architecture session. I'm Rachat from MIT and Jane Street. I'll be chairing the session. We have an absolutely fantastic set of talks for you in this session. And starting us off is Souradip, working on sort of this very interesting problem of trying to program data flow architectures and sort of thinking about how you can take classic ideas in programming languages and imbue them with like some amount of superpowers to bring these kinds of architectures to sort of some amount of sanity. Please take it away, Souradip.
Yep, thanks. Hello, everybody. So Ripple is some work that I did with my advisors, Nathan Beckmann and Brandon Lucia, and an awesome undergraduate at CMU, Yufei. Let's get started. So spatial dataflow architectures, or SDAs, are a general-purpose accelerator platform that runs programs spatially as a dataflow graph across an array of processing elements. SDAs are fast and efficient, but only for some simple regular code. More complex programs can get too big, so they might not fit on the architecture, and they might also get very poor utilization and performance. Our insight is that many of these applications, like this graph traversal on the left, have what we call coarse-grain dataflow behavior, where program regions communicate data to other regions asynchronously, maybe with a work queue or a task pipeline. SDAs should be a great fit here because their hardware pretty much implements exactly these semantics. So what's the problem? Too many SDAs use low-level languages like C, which force the user to write data flow behavior down as a bunch of low-level memory and control flow operations that compile inefficiently. So that graph traversal gets a data flow graph from C that looks like this, which is it's complicated, bloated, and might run pretty slowly. So the problem here is what we call an abstraction inversion. We have a model of data flow behavior in the application and in the hardware, but we lose that information because we lack the software primitives to lower cleanly to SDAs. So our solution here is simple. We want to expose asynchronous data flow semantics of the hardware directly in the language. And so that way the user and the compiler have the primitives to lower efficiently to an SDA. And so Ripple implements this solution. It's a language and architecture that corrects this abstraction inversion. So specifically, Ripple has explicit language support for asynchronous execution, work queues, task pipelines, and synchronizations to program SDAs. And in the architecture, Ripple exposes hardware token queues in its ISA, so that the compiler can achieve a nearly one-to-one mapping of Ripple code to existing SDA hardware. So that same graph traversal compiled from Ripple is going to be much faster and much smaller than the one compiled from C. And the trend is clear on a variety of workloads. So Ripple is on average 3 times faster and nearly halves the program size compared to a state-of-the-art SDA that compiles from C. So for the rest of this talk, we'll look at how SDAs work, the abstraction inversion problem, how Ripple solves it, and some results. So let's highlight a couple of key basics about SDAs. So spatial dataflow architectures compile some code to a dataflow graph of dependent instructions. And that DFG is mapped to a spatial fabric of PEs, each of which runs like a handful of instructions or even sometimes a single instruction for the duration of a program. Instructions talk to each other directly through a network on chip. And so if we zoom in slightly, we'll see hardware queues at each PE. And these queues automatically manage input data that's coming in for each instruction. And so an important takeaway here is that instructions are communicating their inputs and outputs using hardware queues. This is ubiquitous in all SDAs, and it's going to be a point that we'll come back to later. All right, so if you want to run a program, SDAs use what we call the data flow firing rule. And so there's no instruction stream or program counter. Instead, inputs arrive and queue asynchronously at a PE. Instructions then fire whenever all their input data or tokens, which are the gold circles, are available. And independent instructions can fire in parallel. And so tokens sent between instructions are automatically received and drained by hardware queues. The last piece we'll look at is how SDAs get high performance. And it's because of instruction-level parallelism and pipelining. So to give an example, we got a simple for loop here in some C-like code. And then we'll compile it to a DFG, which has this kind of concise and simple pipeline structure with an iterator at the top and a multiply and a store. We'll kick off this loop and map what happens with each instruction using a pipeline diagram that we'll organize into time steps. And so if we kick off the iterator, it produces I equals 0. And then as tokens flow downstream, we'll notice that more and more instructions are ready to fire. And the loop iterator also keeps firing again and again, kicking off more loop iterations. And so this is pipelining. And the SDA is doing it at the loop level. And so this kind of filled out pipeline diagram is exactly what we want to see for all of our applications. And so good pipeline parallelism means that we'll get good IPC, utilization, performance, and that's what we're going to try to achieve with Ripple. All in all, we saw that when done right, SDAs can really exploit this asynchronous pipeline parallelism for good performance. So the abstraction inversion problem in SDAs cuts right into that, squandering a lot of that good pipeline parallelism. So let's take a look at how that happens. So to demonstrate the problem, we'll complicate our example a little bit. We'll use breadth-first search, or BFS, as the example. So for an input graph, we'll try to calculate the BFS tree corresponding to the search, represented by this parents array. We'll have some outstanding vertices to visit along the way, which we'll track at the bottom. And just to be clear, the graph on the left here is the input to the application. It's not a DFG. OK, so BFS is essentially the following steps. We're going to grab a vertex, like 1, and then we'll filter for unvisited neighbors for those vertices, like the bright red ones. We'll set the parents of those neighbors, and then we'll need to traverse vertices again, which we'll track using a work queue. And so this process continues until we're done with the traversal. So BFS here is essentially a set of pipeline stages that are dynamically communicating with each other. This here is coarse-grain data flow behavior. And so SDAs should be great at BFS, because we should be able to pipeline as much work as possible through each stage by continuously dequeuing and enqueuing work through BFS's work queue. And more importantly, SDAs should be really good at handling BFS, because the work queue could be handled by a hardware queue. So unfortunately, though, many SDAs, like the prior work on the right, compile their programs from C or C-like code, which lacks abstraction for data flow semantics. And so in C, if we write that asynchronous communication with a work queue down, it's going to be a full software queue using an array in memory and push and pop methods. Operating on that queue is just as rudimentary. We're going to need something like an irregular while loop because we can't express an automated pipeline with concurrent push and pop. And so what we've done here is the C code has inverted the abstraction of queue-based asynchronous communication. And that a data flow architecture should be able to easily implement this with existing hardware. There's also a lot of consequences in compilation. So the abstraction inversion forces the compiler to implement a lot of low-level memory and control flow instructions of the software queue, instead of reasoning about the high-level coarse-grained data flow behavior in BFS. And so this is detrimental for a number of reasons, mainly memory ordering. Memory ordering is something that a data flow compiler implements when they have a lot of potentially aliasing and racing memory operations, and the compiler serializes them by adding a lot of control flow to preserve sequential memory semantics. And so this happens in BFS. So for instance, in this for loop, so remember that the SDA is going to try to pipeline iterations of this loop. But we have a racing read modify write to parents that exists across loop iterations. And so load in a later iteration might read a stale value before an earlier iteration finishes updates. And so a compiler is going to look at this, and it's going to serialize by adding control flow instructions, which we represent with this red arc here. Also, since the SDA is going to try to pipeline the outer loop as well, push and pop are also ordered to ensure that we don't pop from an empty queue. And so here the impact is a lot worse, actually, on program size and performance, because longer ordering arcs need even more control flow, because we need to route signals inside and outside of control structures in the code. And so the result is this monster-looking DFG that we saw at the beginning. We've caused one of the two major problems in SDAs. The program is way too big. And so in particular, the bold-bordered red nodes, especially on the right side of the graph, are inserted for ordering only on the software queue, which already itself takes a lot of instructions to implement. And so a bloated DFG like this might not even fit on the fabric. All right. Compiling from C also causes another major problem of low utilization and performance. And so I'll try to demonstrate this with BFS running on this input graph. And we're going to try to mark what happens using a pipeline diagram with different parts of the C implementation. This is what we want to have happen. We want to have this perfect pipelining where we pop a vertex, we're going to iterate over its neighbors, and we're going to update parents. And then on the side of the work queue, we want the same kind of thing. As soon as we enqueue a vertex, we want to dequeue it and extend this pipelining from push to pop. But in reality, that's not what we get. So updates to parents are serialized in that for loop that you can see in the third and fourth row of the diagram. And so we lose some pipelining there. But ordering push and pop is even worse. So memory ordering here forces each outer loop iteration to finish before the next one starts, and we can pop again. So we serialize the entire loop nest. And so all the gaps in the diagram are indications of low ILP and utilization. And so that means that if we compile from C, we're going to eliminate all the nice pipelining that we have. All right, let's see what RIPL does about the problem. So RIPL is a language in ISA that corrects the abstraction inversion. RIPL structures programs as asynchronous regions that communicate via queues. And so these queues can be lowered to hardware queues in the architecture. So for BFS, it allows communication between each step, including and especially the work queue, to lower directly to a hardware queue. RIPL enables us to cut straight through the software queue implementation in C, its API, and the irregular while loop. And instead, we can write down traversal logic using RIPL's asynchronous iterators, or asyncs. So in RIPL, users distribute code into asyncs that run asynchronously from each other and run in parallel. And so here, BFS has two asyncs, one for initialization and one for the bulk of the work. So let's dive into some of the key properties of an async and RIPL's push primitive. So asyncs have a name, an input list, and a body of code. And an async defines an implicit queue of inputs that it iterates over, executing the body for each input set. And so inputs to that queue arrive asynchronously. And each iteration launched is something that we call a task. And so each inputs drain automatically, meaning that we're going to launch some tasks, and those tasks are going to pipeline. Push is our primitive to define a data flow dependence between asyncs. And so that allows for direct asynchronous communication of data between them. And so in our case, queue pushes to itself. And so if you put all of these components together, we can drain the vertices into tasks of the async queue, pipeline them, concurrently add work back to the queue using push. And so a lot of these semantics should seem familiar. So if we look back into SDA land, we can see that an async captures the semantics of asynchrony, queuing, and pipelining semantics that data flow execution and hardware queues have. And push defines a dependence that's effectively a DFG edge. All right, so let's see how the RIPL ISA implements async and push. So RIPL builds on a recent dataflow ISA called Riptide. We borrow its arithmetic control flow and memory instructions, but we also expose hardware queues and token arbitration in its ISA by adding queue and arbiter instructions. So queue here defines a hardware queue, and an arbiter performs round-robin selection of inputs to feed a queue. And so if we revisit BFS, we can see how this works. So remember that BFS has these two asyncs. And async inputs here for a queue are going to map directly to a queue instruction. Pushes map the DFG arcs into an arbiter, which selects an input to pass along. And so the entirety of BFS's work queue can just be captured using two instructions. And so now you might be wondering why we need a queue instruction at all if RIPL maps data flow to existing hardware queues. Most of the time we don't. The compiler can actually fold the queue instruction into hardware queues of downstream operations. But in certain cases we can't, when we can't bound the size of the queue. So BFS actually exhibits this property. So BFS has the thing where we push work from the queue back to itself. And if the queue were mapped onto a hardware queue, it could deadlock if that queue fills up. And so we could implement the work queue with loads and stores, but that has all the problems that C had. What we do instead is we add spilling to the queue instruction. So a single queue instruction can dynamically spill to memory as needed to avoid deadlock. And so RIPL's compiler here is going to identify queues to spill. And RIPL's microarchitecture supports spilling with minor changes. But I'll leave some of those details for the paper. But supporting cycles here really expands the scope of programs that RIPL can implement. And so this is a key advantage over prior data flow languages, which I'll talk about a little bit later. So that covers async and push. But RIPL provides even more primitives to enable more pipelining. So for instance, if you remember, RIPL and the C program had this race on updates to parents here, which requires ordering that still hurts pipelining. To eliminate these ordering edges, RIPL provides atomics. And so atomics acquire a set of input addresses, like parent sub NB. It executes the body, and it releases those addresses implicitly. Atomics dynamically order racing accesses to parent sub NB, which are rare in this case. And we've designed the architecture for RIPL so that they pipeline. And so that enables a lot of performance. And you can also read about that in the paper. So by solving the abstraction inversion problem, Ripple generates a fast and concise program for BFS. All right, let's try and put this all together. So remember this from the C implementation, which is how C was performing on BFS. Ripple improves over that by eliminating all the stalls in the C version of the program to perfectly pipeline using tasks and atomics. All right, so now we've seen how Ripple works. I wanted to talk a little bit about why you should use it to program SDAs over other options. So there's been a lot of asynchronous programming languages. And these languages are great, but they don't exactly solve the abstraction inversion problem for SDAs. So some of those primitives in those languages might mismatch by offering too much or too little by way of semantics. And so channels in Go can be manipulated, for instance, instantiated and used arbitrarily, but Ripple queues only support push with automatic task spawning semantics that matches like the underlying SDA hardware. And so there's also been only a few dataflow languages, and all of those have limitations as well. And I'll skip over those in the interest of time. But Ripple here gives you only a few primitives, so you can express exactly the dataflow semantics supported by SDA hardware. And so there's a detailed discussion of that in the paper, which I'll leave for now. And you can read a lot more about it, the architecture and whatnot in the paper as well. All right, let's look at some results. So we evaluated a variety of workloads using real and synthetic inputs, and we compared to two systems, Riptide, a state-of-the-art SDA that compiles from C, and a sequential von Neumann processor, and we simulated these results. So the main takeaway here is that Ripple is fast. So we plotted speedup of Riptide and Ripple over the sequential von Neumann processor. And so these bars here show a geomean speedup of our workloads. And so what you'll see is Riptide is already fast compared to the von Neumann processor, but Ripple achieves way more performance, amounting to a 3 times speedup over Riptide. The rest of the bars here show performance for each workload. Each workload was evaluated on 2 inputs. And if we look at these graph workloads, for instance, we get a lot of performance by eliminating software queues and enabling workless-style parallelism. We get similarly good performance for linear algebra workloads, where we use Ripple to build coarse-grain pipeline stages, which eliminates a lot of the ordering. So Ripple gets big speedups across the board on all of these applications. Our other takeaway is that Ripple programs are small. So here we measure program size as the number of static instructions. And so for instance, for BFS, Ripple, which is abbreviated as RP, more than halves the program size compared to Riptide, which is abbreviated RT. And to understand how Ripple does this, we can split our instructions into control flow versus non-control flow. And Ripple eliminates a lot of the control flow that BFS has in the Riptide and the von Neumann version by getting rid of software queuing and using atomics. And so we see this trend across the board for all of our workloads. On average, Ripple is going to shrink our programs by 1.9 times. All right, so today we looked at Ripple, a language in an ISA that solves the SDA abstraction inversion problem. And it achieves significant performance and program size improvements over the state of the art. Thank you for listening. So I'm open to questions.
Folks, please feel free to raise your hand or stand up, and the volunteers will get you the mics. Question back there.
Yeah, thank you for the great talk. I'm Andy from Georgia Tech. I just had a small question, I guess, about like how you collected your numbers. So,
sure.
Because like I guess Ripple comes with its own ISA and like dedicated architecture. So I guess how did you run everything? I'm assuming some sort of simulation, and like how did you like ensure like a fair comparison between like the CPU, Riptide, and Ripple?
Yeah. So I'll talk about like the way that we simulated is we run the dataflow graph. And we don't do a full system simulation with like energy numbers and hardware and that kind of thing. So this is a higher level microarchitectural simulation. But we had a prior simulator that was built for Riptide, and that was close to the RTL that we implemented. And Ripple borrows from that ISA. It adds a few instructions like for atomics and queuing. And so we've implemented that on top of that simulator. And so we run the dataflow graph and get numbers in that way. The von Neumann processor we're emulating LLVM-IR. And the reason we do that is because those instructions are the closest to the ISA. So if we did something low level like RISC-V, we have stuff like moves and that kind of thing, which dataflow architectures don't have. So that was kind of the fair comparison there.
I'd like to understand better the atomic construct that
Sure.
you have, and to what extent it's compile time versus runtime. Do you have to worry about detecting deadlocks or anything like that?
Yeah, so that's a good question. So we talk about this at length in the paper. I'll answer all the points there. So when you write down an atomic, what the compiler is doing statically is it's looking at the input addresses, and it's implementing memory ordering for the atomics with respect to other atomics and other racing accesses around it. That's one part. The other part is dynamically, we have a hardware directory. And so when you do a set of acquires, we have acquire and release instructions in the architecture. And those are working together with the directory to like dynamically acquire addresses and reserve and release addresses if you need to. There is a possibility of deadlock with atomics. And so we use the same idea of spilling. So basically, if you have two sets of atomics, and they're communicating like a live out from one atomic to another, you could pile up a bunch of tokens and deadlock. And so spilling solves that problem in the same way that we do for tasks.
Any last questions? Sweet. Let's thank the speaker one more time.